Hey everybody, today we're going to show you how to put together some capacitors and resistors and op amps to build what we call active filters. In other words, things that have filtering and gain on them. I'm Michelle Maharbiz.
And I'm Vivek Subramanian. Let's get started. So the key point is we are now going to build filters that will include op amps, hence the name active filters. Okay? And let's start by reviewing a very simple op amp circuit. This is an inverting amplifier that you should have learned about before. You know what the transfer function is. So we want to relate V out to Vs, in other words, find the gain of this amplifier. You know that it's just going to be calculated in this form. Firstly, it's inverting, so there's a minus sign, and it's going to be the resistance of the feedback path, RF, divided by the resistance of the forward path, RS.
I remember that from the basic op amp stuff.
Right, and that's the case here. Now, this particular example is done using resistors, but you'll notice that I've written it as impedances, and the reason is we're now going to bring in a variant on that. Specifically, I'm going to bring in a situation where one or more of the elements, specifically here, one of the elements is frequency dependent. Okay. I'm going to put a capacitor in here. Okay, so if I put a capacitor in here, I can essentially take the same form and now substitute in. RS stays the same, so ZS is still just the resistor value. But if I want to find ZF on the feedback path, it's the parallel combination of the impedance of the resistor and the impedance of the capacitor, which I can calculate, and it turns out to take this form. That is, it's RF over 1 plus J omega RF CF.
Okay.
Okay, so you'll notice, now, seeing this, Michelle, you should automatically recognize that this is therefore going to be frequency dependent.
Oh, that's right. So your V out or V out or Vs is going to be frequency dependent.
Right. Okay. And in fact, if you look at this, given that the gain is supposed to go up with ZF, whereas if I look here, ZF goes down with frequency, I would expect the gain to drop with increasing frequency.
Oh, I get it. So basically you can build an amplifier with a gain that changes with frequency. Okay.
Exactly. That's the basic idea. This is an amplifier, the gain that changes with frequency. What I can do is I can essentially work out what that is by taking my V out equation and plugging in ZF and ZS. And so this is what I get. And so what I get is, firstly, it's an inverting function. Yep. Okay? So I've got RF and RS. And then I have this additional term that corresponds to the frequency dependent elements. Now, think about it. Let's do it qualitatively. At really low frequency, CF becomes?
That's an open.
It's an open.
So it just looks like the old amplifier.
So exactly. So at really low frequencies, this looks just like this, and the gain is minus ZF over ZS. So specifically, minus RF over RS. So we call that the low pass gain. Okay? And then the rest of it, we have this frequency dependent behavior. Michelle, looking at this, what does that look like to you in our Bodhi plot language?
That looks like a pole with a corner frequency of omega LP.
Exactly. That's exactly right.
Shazam!
So, yeah, so what we've got is we've got a low frequency gain, and then we have a corner frequency, and after that it's going to drop off. Michelle, what is the slope in the Bodhi plot for this?
It's got to be minus 20 dB per decade.
Exactly, because it's a first order term. Okay, so you've done this, you've designed your first filter. It's an active low pass filter. At low frequencies, it's going to have a gain of minus RF over RS, and then at the corner frequency, it's going to turn down, and it's going to drop at 20 dB per decade, and the corner frequency point is given by this equation.
This is pretty cool. So in Bodhi land, I would be adding these two terms, right? Because when I turn them into dBs.
Exactly.
So this is like our K in that old lookup.
Yeah, so it'll shift it up and down.
20 log 10 of this.
Exactly.
Plus the standard pole. Okay, cool. That was pretty neat. Let's do high pass. So we'll move through this a bit quicker. In the high pass case, we put the capacitor in series with the resistor at the input.
Okay, let me try to do this qualitatively. Okay. So I still have the same equation for calculating the gain, so it's minus ZF over ZS, but now my ZS goes down with frequency, so that should cause my gain to go up with frequency.
That's right. That's why it's a high pass filter.
Aha.
Aha. Now here we have our old gain function, which by the way always looks like, in these cases, always looks like the basic gain function, right? This is not frequency dependent. But this looks like what? What two terms are in this transfer function?
So, but now to be clear, the difference here is now this is the frequency, this is the gain at high frequency.
Right.
And that's why, and at high frequencies, the CS disappears.
That's right.
So, okay, got it. All right, and now I'm looking at that. Well, the numerator looks like a 0 at the origin, and the denominator looks like a simple pole. So what that should do is go up with frequency till I hit that high pass point, and then it'll level out. and it's going to go up at 20 dB per decade because of the zero at the origin, and then it's going to level out to being flat because of the simple pole.
Voila.
Easy.
Perfect. And the corner frequency is given to you again by RSCS. Okay?
That's cool. All right.
Pretty easy to design these things. So since it's so easy to design these things, right, what can we do with them?
Well, we can start building more complex functions. So, for example, if you think about it, what I can do is if I have a low-pass filter, which cuts off stuff below a certain frequency and passes stuff above it, I can cascade that with a high-pass filter, which cuts off stuff above a certain frequency. If the low-pass filter cutoff is positioned such that it is above the high-pass filter cutoff, what we get is something like this. The low-pass allows through everything to the left of omega LP. The that all goes to the high-pass filter. Then the high-pass filter will allow everything to the right of omega HP. So effectively, I make a bandpass filter.
Right, you're chopping off, one thing chops off the left side, the other chops off the right, and together they leave the middle.
Right. If you position them correctly, in other words, you got to make sure the low pass is above the high pass in terms of the frequency cutoffs, then you'll get a bandpass filter.
Makes sense. And by feeding them and you cascading them, you just mean the output of, in this case, the output of the low pass is
Fed
connected
into
to the input.
Exactly.
So I have another question. Why can't we just do this? Why do we need op amps to do this? Why couldn't we just take a low pass filter and a high pass filter of the sort of passive kind?
Well, there's the one big reason is, of course, that when we start putting all these filters end to end, they each are sort of attenuating the signal a little bit.
It's the fact that these have gain in both of them that allows you to adjust all of it so that the part that you're passing, you boost
Keep it
back
up.
up to 1.
That's right.
Because each one kills a little bit of it.
Correct. That's right. And then remember, the moment we have, if we were trying to do this just passively with multiple RC circuits, when you're calculating the transfer functions, it's not as simple as it was earlier. They can be second order interactions.
That's right, because each op amp is effectively sort of high impedancing from the thing before.
Exactly. Okay.
Always thinking, always thinking.
Right. Now, we can do the complement, namely the band reject filter, by setting them up such that the low-pass filter and the high-pass filter are chosen. Now we'll switch the positions of the cutoff points. So the low-pass will be below the high-pass, and then we'll sum them. So what the low-pass do is it allows through everything to the left of omega LP. The high-pass allows everything to the right of omega HP. Here, omega HP is positioned above omega LP, so when we sum the two, what we're going to get is we allow this stuff through, and we allow this stuff through, but the stuff here that neither filter allows through gets blocked. And we call that the band stop or band reject.
Perfect.
All right? So that's the basic idea. Now, Michelle, I have a thought.
You have a thought?
Yes, and my thought is the following. Given that each of these is contributing, assuming these are first order terms, each is contributing a 20 dB per decade slope on its edge, could you do something to get steeper filters?
Dun dun. Boom, you can. So, you can take filters that have the same corner frequency.
All right, so they're all at 10 to the 5 radians per second.
Right, and each one would normally, say in the case of these low-pass filters, would roll off at 20 dB per decade, right?
Yep.
But I cascade them. So each one essentially serves to steepen the roll-off rate.
I got it.
Okay, so if I just was using V1 as my output, I would have a low-pass filter that would roll off and I get minus 20 dB a decade. But now with 2 of them, it's rolling off at minus 40, and with 3 of them, it's rolling off minus 60. Now notice though, just to be completely clear, you see each of these has the exact low-pass or cutoff frequency independently, but together they are in fact shifting the combined cutoff frequency slightly as well. So they're dropping. The 3 dB point for the combined thing is here, but if you go back to the original curve, it's much lower. So in other words, you're also shifting the corner of the combined thing.
Right, and that makes sense because what I'm doing, the 3 dB point falls within the shoulder region, so it would make sense for that to happen.
That's right. And of course, you can, you notice in our little drawing, one of them has a really big gain of 1,000. And then the others are 1. And
right.
So basically you can use one or a combination of them to kind of beef up your gain to whatever you want.
Right. And remember, this is the beauty of these systems. If you tried to do this passively, each of these would cut off more of the signal. Whereas here we can have a really high gain to begin with, and then if there's any attenuation in the others, we still end up with a net pretty good filter.
Right, or backwards, right? Vivek, you're kind of an expert on this. I mean, I could have the front end one have kind of a crappy gain, but a very, very good input impedance, and then
you can arrange them as you need to. Okay, but let's try to work through a more complex example now. And let's do an example of designing an arbitrary band reject filter. Okay, so here's the specs I'm going to give you. I'm going to say I want a gain of a certain amount, and specifically ask for a gain of -50. And I'm going to tell you what I want the corners to be, so 20 kilohertz to 40 kilohertz for that stop band. And I want a second order filter.
Okay, wait, before you put anything on the screen. So the part C, if I want a second order filter, and I remember band rejects are composed of sort of a low pass branch and a high pass branch,
and then you sum them, right?
So which means, but I want a 40 dB per decade drop, which means that the low pass band is going to have 2 filters to give me the 40, just as we did in the last slide, and then a high pass band better to do the same thing.
Right, so you would expect to have 4 filters total. 2 low pass, 2 high pass. The 2 low pass will be put in series, the 2 high pass will be put in series, and the outputs of those individual chains will be summed.
And we could split the gain amongst all of these things, but it might be easier, and also wouldn't have to worry about sort of component matching if everything is one but the summer, and then the summer can do all the gain.
And exactly. So you got it. Here's what we're going to do. We'll have 2 low passes, 2 high passes. The use of these 2 low passes together gives us the 40 dB per decade. The use of the 2 high passes together gives us the 40 dB per decade. We'll pick the values, so you see that we set it up for 20 kilohertz and 40 kilohertz. I've converted it into radians per second. Okay, and then I'll sum them together. All of these have gains of 1, and then I get the gain of 50 by putting the summing amplifier with the gain.
It may be useful to back up in the video 2 slides ago where we showed you the band reject filter curve, so you see what we mean by this. So let's take a second to do this.
So here's the low pass, the band, and here's the high pass in a standard band reject, and you see how we sum them. And if we go forward,
and this is what you meant by 40 dB drop, right? Basically the steepness of this.
Yeah, we need it to be 40 dB. And if you go to the next slide, here you see how we get the 40 dB. We take 2 first order filters, which just look like this, which have a single capacitive element, and we put them in series. Okay, let's move forward. Now, let's go ahead and look at the op-amp version. So you see that we have the circuits as set up here. We have individual low-pass filters and individual high-pass filters of the type we've already looked at. We've got them connected end to end so that we get the second order behavior, and then we sum them, and then we have a gain element. Okay, now I'm going to start by just making somewhat of an, there's a huge amount of design space, so I'm going to make some number choice to start, and I'm going to pick to start with an R value of 1K. Okay, and I've picked all the R's to be the same just because I want to. Okay, I could have done it other ways. Once I know the value of R from the equations for the omega LP and omega HP, I can figure out the values of the capacitances that I need for the low-pass filters and the high-pass filters respectively. Remember, these two need to be coincident with respect to their cutoff frequencies so that I get that second order behavior. Okay, and similarly over here. That gives me what I need to get the shoulders that I want. Then finally, I just need to figure out what I want to do here to get the gain of 50. Well, that's easy. I know the value of R coming in. This is just a summing amplifier. So going back way back to the op-amp module, I can figure out what RF I need, and it turns out I'm going to need a value of 50K. And that makes sense because I have an R of 1K.
Got it.
Okay? What I can do then is I can put all of these together, and I can figure out the transfer function. Now, the transfer function, let's do it qualitatively first. The transfer function is going to be the net result of that big summing amplifier. There's no frequency-dependent elements in the summing amplifier, so that's going to give us that big gain. And then we have 2 low-pass and 2 high-pass filters set up with coincident corner frequencies for the low-pass and coincident corner frequencies for the high-pass. So we'll get second-order term contributions from each of those. Okay? So that's what we get overall. So
that's the transfer
this is the gain, this is the summing behavior, and the squares are because we have 2 low-pass and 2 high-pass respectively. And so you can see this is what the transfer function works out to be.
Can we plot that?
Yeah, we can. And let's go ahead and do that. And that's right here.
Oh, okay. So basically, we get kind of what we were sort of expecting, right? We get our low-pass filter on the left, our high-pass filter on the right, and the overlap kind of gives us or the lack of overlap gives us the notch that we wanted. We got the gain that we wanted, right? That's the right up here, right? And the transfer function is down here. Okay, so it kind of worked out like we wanted.
Yeah. So these active filters are pretty nice because you can break things up into individual parts and sort of design each part carefully, and so you can build more sophisticated elements this way. They work great. Remember, but one of the things we sort of glossed over, and if you take more advanced classes, you learn about this. In all this analysis, we assume the op-amps themselves have no frequency dependent. In other words, they're essentially perfect.
Right.
And that is one of the complications in real active filter design, is the op amps themselves are not perfect.
That's right, because they're made of transistors, and those transistors have associated capacitances, and they contribute poles and zeros to the behavior. As a quick application note, one of the uses of things like this, these sometimes are called notch filters, is basically to isolate out some frequency you really don't want. And an example of that is 60 hertz.
Why would that be, Michelle?
Because it's everywhere, and you don't want it to pollute.
And it's everywhere, right? And it's everywhere because it's what we use for power transmission.
That's right. It's everywhere because it's in your power lines. Okay. Thanks for sticking with us, and we'll see you soon.